you cannot just say, oh, well, it's going to be the change in potential energy equals the change in kinetic energy, and then that's going to be 1/2 mv squared delta v, and take delta v plus 5, and that's going to be your answer. You can't do that. Okay? You can't do that. You have to take all of the kinetic energy and all of the potential energy and turn it into all of the new kinetic energy. Does that make sense?
Yes.
So this will be, so I'll show you. Let's just show you how that works. So at the top, we're 20 meters up. We go down. So we got a initial V1 of 5 meters and D1 of 20 meters, 5 meters, 20 meters. And then here, D2 is going to be 0 meters. Can you determine how fast it's going to be going? D2 at the bottom?
Well, D2 is a change from 20 to V2.
Well, why don't you take out your calculator and find it out? We'll just pause for a second and take out your calculator and bang in your calculator and see if we can figure out how fast it'd be going at D2. Oh, by the way, does the mass matter? Let's throw a mass in there just in case, and we'll see if it matters later on. So what do you want the mass of the object to be?
5 kilograms.
5 kilograms. Okay. Do you want me to write your formulas in for you?
Yeah. Yes.
Okay, just easier if they're in front of you on the board. So kinetic energy is 1/2 mv squared, and potential energy equals mgh. Can you see that in the back? Okay, my green pen
M is mass, right?
M is mass. Yes, good point. We're going to assume this is on Earth. Look at all those 5s. Got some weird numbers.
Hold on, man. Hold on.
Okay, holding on.
So that's the mass. That's 5 kilograms.
That's what I got.
Well, yeah. See that formula. Hold on, man.
Holding on. Wait a minute.
Is that
There's a lot of stuff going on here.
Is that the D1?
Chris,
is that
what did
the
you
height,
get?
Or is that?
D1 is the height, yes. So there's a change. There's a change of 20 meters. So
Hey, Chris,
this is
what did you
20
get?
meters from where you're starting to where you're ending. All right.
Are we supposed to use that equation too right there?
Yes.
Okay.
And we're assuming that's frictionless, obviously, because we're not going to throw any friction in there yet.
Is the one on the left.
Oh.
Are we supposed to use, no, we want
Just occurred to me the camera actually might not be seeing us.
Not true. Not true.
I think it is.
Oh, I was just seeing the edge. Yeah, we're good. You got an answer? Something you do.
106.2.5.
I already know.
Kinetic energy I got.
We're looking for velocity.
The velocity I got was 20 meters per
20 meters per second. Okay, so one option is 20 meters per second. Anyone else have anything besides 20 meters per second? Something maybe a little more precise? 19.4 meters per second. Anything else?
You got it.
Well, you just did the left side, we're gonna do the right side.
Okay. All right, so a few of you got this. A few were like, I'm not going to answer because I don't want to sound like I'm stupid. You know, my fragile adolescent ego. So PE initially, again, it's up here at 20 meters. So PE is mgh 1/2 mv squared for KE. Okay. So mgh, what's m here? 5, and then g is
-10.
10. Let's just make it 10. Okay. Up there. And h is 20 plus 1/2. What's m? 5. And then what's v?
5 squared.
Look at all the 5s. And this is a lot. So we got a total energy. Can you give me what the total energy is? This is TME. 1062. 2.5. All right, that's a lot of significant digits, but whatever. And the units is joules. Okay. So this is the total mechanical energy everywhere in the path. If we're ignoring friction, does that TME change? No. Okay. That total mechanical energy is going to be conserved everywhere in the path, including the bottom, as long as we're ignoring friction. And we will, almost always. So now over here, what this means is this KE2 plus PE2 has to equal 1062.5. Because that's the TME, total mechanical energy. Make sense?
Yeah.
Okay, so PE, mass is 5, gravity is 10. What's the height? 0. Plus KE, 1/2, mass is 5, times V squared is what we're looking for. Just solve for V squared. So that looks like, to me, yeah, so this is 2.5, so that divided by 2.5 square root?
20.6.
20.6.
I was close.
You were close.
Wrong.
Okay.
I forgot to have the kinetic.
Make sense? Okay, now, let this absorb in for a few seconds. Oh, I should put the unit in there. Oh, I did, meters per second. Let this absorb in for a few seconds, then I'll ask you an important question.
Oh, I got the answer. Cool. I learned how to do it.
All right. So, ready?
Yes.
If this was atom, either one,
5 kilograms.
atoms get to the bottom at 20.6 meters per second. Make sense? What if, does that make sense?
Yes.
What if it's not atom, what if it's big fat buyers? Will buyers, oh he has facial hair, glasses. Okay, would my velocity be the same at the bottom?
Yes. No.
When you go to Disneyland, do they have to weigh you before you get on the rides?
No.
Yeah. Something. No.
Really?
There's some rides.
That's never happened to me before.
Wait,
Never.
Did someone say, nah, you can
Okay.
be 3,000?
They're like, sorry fatty, you can't get on this ride.
No, just
you guys are the
they
things
make
of
you-
the Americans with Disabilities Act, right?
They make you weigh yourself at Wet n Wild.
Really?
Yeah.
Yeah, water.
Gross. Okay, anyway, so does mass matter?
Yes. Low key.
Yes.
Yeah.
Chat with your neighbor. Take a minute and chat with your neighbor as I write a formula down.
What is the potential energy is gas?
I've been cowboy.
debate. They never had a weight thing. They probably thought you're fat.
No, on
They're
the
like, you didn't need fat, you need to weigh
on the
yourself.
one that goes like, because everything was stale on recently because people are going above the equal swing.
No, because this side of the head, you have to get it.
They're floor.
It should be
Yeah, because I've really seen people like go to the nerds and talk like,
Yeah, I get it.
So, if you believe math matters, raise your hand. If you believe math doesn't matter, raise your hand. It doesn't matter. So, look at this formula. Could you not just cancel out mass and mass and mass
both sides
mass?
equation.
Yeah, you remove them from all terms in the equation, and this just becomes GH1 plus 1/2 V squared 1 equals GH2 plus 1/2 V squared 2.
Dirty dog. You dumb, dirty dog.
This is why they don't bother to weigh you if they know what they're doing.
I don't know why they would weigh you with.
No.
They weigh you down the slide.
See if you can fit down the slide. That's more circumference. That would be ultimately insulting if they're like, "Come here, fatty," and they ring around. Can you like put a ring over you? Like, so can you fit
I
it?
think it's a change in mass because they only do it when I'm like with my little sisters.
Oh, make sure you don't lose anybody. It's like you went down with 2 people, you went down with 2, and you ended up
Yeah,
with
so
1.
make sure you don't like go
If you
above
go
the
down,
half height
yeah,
and also
double
make
that.
sure you don't get stuck.
Yeah, the ride I count on debate, there were like people going above it or they wouldn't weigh enough, so then they'd get stuck.
Would that matter though?
Dark in there, I can see.
What the?
Because there's one.
You set one person down.
When you go to a skate park, do they have like this is the half pipe for the fatties and this is the half pipe for the skinny kids?
I mean, yeah.
It's just one half pipe, right?
It's more of a socials construct.
Yeah, exactly. I think they're just trying to make you uncomfortable. So you're already in a bathing suit. Sorry, fatty. We don't want to. People are taking pictures. We gotta.
We got
Whaley, we have
season.
3 away from what's going on?
we have a image to maintain.
Ready to hop balloons.
Yeah. Okay, so anyway, so vertical movement, again, you probably already figured this out. I'm not going to go spend a lot of time on it. When you throw something up, it has no kinetic at the beginning and no potential at the beginning. You give it some oomph, it has maximum kinetic at the moment right after you throw it, and no potential. And at the top, what does it have only? At the very top.
Potential.
Only potential, right? Again, as long as it's vertical movement, you're going to have only potential and no kinetic. So maximum potential, 0 kinetic, somewhere between the 2 in here. And how would you be able to find PE and KE if you needed to? Just use your formulas, right? Change in height, whatever the height is. Roller coaster. Ooh, I got a movie. I wonder if it works. A lot of these movies don't work because of Windows 10 and Office, whatever Office version this is, but we'll see if this one works. It appears to be working. Let's see. And look at that, it's not working. Okay. Don't cry. I know there is one that will work, and you're gonna love it. All right. So, animation. So more work energy animations. How much time do I want to spend on this?
Bang, bang, boom, booms.
Yeah, I don't want to do anything on this one. This one, however, is pretty cool. All right. So a pendulum. We have an entire unit over pendulums and springs. Anyway, you can call it pendulum or pendulum. If you want to sound really cool, call it pendulum.
Pendulum.
Pendulum. A pendulum.
Like,
You sound like you're just work for
Pendulum or something. It's like
All
people that say
right.
leave.
So take a look at this. This is actually kind of a neat animation, and it's slowed down for us. Thank goodness.
Lever or lever.
Does this object ever get 0 potential energy?
well, yeah.
No.
What?
No. Why?
Oh, because it's still off the ground.
Yeah, it's not. A pendulum can't
Oh,
strike the ground, right?
Yeah.
If it strikes the ground, you have a problem. So the only way you can make it have 0 is if you put the reference point right there. So it's always got a tiny bit of height that it's going over. So there's the height right there. So look what happens with the velocity here. So velocity up here is 0, approximately. And where's velocity maximum?
At the bottom.
At the bottom. Velocity is maximum at the bottom because your kinetic energy is maximum at the bottom. Up here you have only potential energy. Down here you have mostly kinetic and 0 kinetic up here. So whatever change in kinetic you have from here to here is going to be the change in potential energy from here to here. I'll say it again. With whatever change in kinetic you have from here to here is going to be the change in potential from here to here. It's just going to be the same. Okay. As long as we ignore air resistance. Do we like to ignore air resistance?
Yes.
Yeah, that's a good.
Oh, what was that physics thing I saw?
Yeah, I like it.
You've seen
All right. So now that you've done
There's
this,
no quizzing, but
guys,
there's no.
now that you've done this, can you determine what V is here? What is
I
V?
will attempt to use
Right
my
there.
big brain.
This is 2 meters. And down here, the PE up there is 2 meters from here to here, which is the reference point. And the PE is, well, the height here is 0.5 meters. This is 0.5.
It says it goes around 5.670 meters per second. At the bottom.
So, can you figure out how fast it's going? It's going from 2 meters to 0.5 meters. Doesn't look like 0.5 meters, but it is. So 2 meters to 0.5 meters. How fast is it going? Or what's the, yeah, it's down there. It's also in the animation, but take a look.
So position 1 is at the top of the application.
The velocity is very different.
I love how they made it a capital B for Bob. A capital B for Bob. It's like, so usually they're called the Bobs, whatever it's called, Bob. They made a capital. They named it. They named their pendulum.
Also capitalized
This was done in a program called Interactive Physics, and it's a pretty cool, really, really old program. That it was the PhET simulation of its day. Teachers who had computers would use interactive physics with kids.
Was this done on the moon?
Maybe. So MGH, M here. Does it matter what the M is?
Nope.
We just get rid of it, or make it 1. Okay. So G is going to be 10. Height is going to be 2 meters. Plus 1/2, and V is 0. Comes to a stop, right? So what is the total mechanical energy at the top? How much?
20.
Are you sure? It seems like a lot. 20 joules?
Yes, 20
20 joules. All right. So it's 20 joules, which means down here this must also equal 20 joules because this is the conservation of energy, yeah?
Yeah.
All right. So G is still 10. Height is now 0.5 plus 1/2 V squared equals 20. Is this math you can do?
Yeah.
Yeah. So what's the V?
2.8.
2.8?
Yeah.
I don't know. I actually haven't done it. Does anybody else want to confirm Kate's answer?
I can hear Kate's answer, so
How much?
2.7.
2.7? What that?
Really? Really? 2.7? Are you sure?
Hey, don't fight. Don't fight. Wait after school.
Yeah.
We'll settle this in the octagon.
Meeting at the bro.
Okay, does this make sense? Is this math you can do?
Yeah.
This is math you can do? Okay. So again, the important thing is you got to look at the potential and kinetic at one point and the potential and kinetic at another point. If you're doing that, you're going to be in great shape. Again, I haven't actually done this. I haven't checked their work, but yeah, between Charles and Kate, it seems like you guys got the right answer.
Mm.
Right. This is something we're actually going to do in a lab. One of my favorite labs we do, and I love this lab. We're going to take a race car at an angle. Well, you're all going to take race cars at an angle, and then you're going to make a little paper box, and you're going to roll the car down a ramp into the paper box, and then you're going to collect a bunch of data about the paper box. You see what's going on here?
Yeah.
The car's got a whole bunch of kinetic energy. We'll wait for the restart. A whole bunch of kinetic energy. It goes down the ramp with its kinetic energy, and then at the bottom, all of the potential is turned into kinetic, and it grabs the box, and the box slides, and all that kinetic is arrested into friction, which is cute.
Gotta be fake friction.
All right, I know these work. These are WMVs. So,
Yeah, if they don't work, then there's a problem.
They don't work.
yes.
Oh, do a trick.
To do what?
Do a trick.
All right, who's skateboarding in here? Who's a skateboarder?
Just Adam.
So Adam's a skateboarder. So now that Adam has a decent understanding of conservation of energy, we can do this animation. So he's way up there, way up there, like 30 meters up. He's like all mess with death because devil may care, here I come. So down he goes, woohoo! Then he goes across the jump, woohoo! And then he's like, I'm cool, and he goes up, and he comes back up, woohoo! Boom! Now, if we ignore friction, this is a very important video, so pay attention. If we ignore friction, which we can't, but in real life, but pretend we can, then if he started at 30 meters, how high is he now? 30 meters, right? So if he started at 30 meters, he's going to go down, he's going to end up at 30 meters, ignoring friction, right? Now let's back it up a little bit. So, my mouse. Let's back it up a little bit.
But yeah, didn't he gain?
So he's like,
Think of 30 meters.
so he starts up at 30 meters. Woohoo, I am so awesome! And he jumps up and then he's at the midway there. Is he at 30 meters?
No.
Talk about your neighbor. So he's at the middle point, so his path looks like this. It goes down, up, and down again. Is that 30 meters?
No.
No. Why?